Okay, so in this video we're going to be talking about free-falling objects. Similar to projectiles in one dimension, which I mentioned, or I talked about in the previous video, but the difference here is they're actually kind of exactly the opposite. For projectiles in one dimension, you're throwing it up and throwing it upwards, and when it reaches the top at the maximum height, the velocity is going to be 0. Well, for free falling, you're dropping them, right? You're dropping the object. So actually the initial velocity in this case is going to be 0. So we can illustrate that with the following problems. First one, we have a quarter dropped from 400 meters above the ground. It's pretty high up. With what velocity will it hit the ground? So you're dropping it, that's key, dropping it from 400 meters above the ground. With what velocity will it hit the ground? So again, your key word here is dropped. That immediately tells you that your initial velocity is equal to 0. So in trying to decide what kinematic equation you want to use, we know our acceleration, right? If you're dropping anything on Earth, it's going to be acted on by the force of gravity. We have the displacement, that's 400 meters. We were told that in the problem. And we have our V initial, right? And we're trying to solve for our V final. So to me, it seems like we should use this equation. V final squared is equal to V initial squared plus 2a delta y. Again, delta y in this case just because naturally you're using a vertical axis, right? But you can set it to delta x if you state that the axis you're using puts x on the vertical rather than the horizontal. So that's completely up to you. Ultimately, it doesn't matter, but in this case, I'm going to go with delta y for our displacement. So our V initial, as we stated earlier, is equal to 0. Our x initial is equal to whatever we set it to. So it could either be 0 or it could be 400. In this case, to make it more complicated, let's just set it to 0. Which means our x final is going to be 400. Which means when you're going down to the positive, and when you're going up, you're going to the negative. And that's just how I decided to set my axis. And again, you can set that however you like. Because going down is towards the positive, right? Then our acceleration, or gravity, is going to be positive 9.81 meters per second squared. If I had said that the positive was going up, then our gravity would be negative because it would be acting in the opposite direction. In this case, gravity is working in the same direction as the positive side of our axis. So you have to keep that in mind, because if you switch around your signs, it seems like a little thing, but at the end it can really change your problem and ultimately make you get the wrong answer. So now let us plug in what we know. So again, we're using this equation right here. So V final squared, which is what we're trying to solve for, is equal to 0 plus 2 positive 9.81 meters per second squared and 400 meters. Positive 400 meters because we're going down to the positive. When you solve for both sides solve for the final velocity, which it's set up in a way that is very easy for us to do, all we have to do is square root both sides. and we are going to get that V final is equal to 88.6 meters per second. So the key to solving this problem is understanding that when you drop an object, your initial velocity is going to be 0. Let's go to part 2, or number 2. Different question. If you drop a penny on a planet with a gravity constant of negative 1.5 meters per second squared, and you drop it into a crevice that's 120 meters, how long will it take to hit the bottom? So in this case, we're not solving for the final velocity, at least at first, right? The first, we're trying to solve for the amount of time. So you have to think about what kind of kinematic equation you want to use to solve this problem. Clearly, if we are solving for time, you want to eventually use an equation that has time as a variable. Now let me not confuse you. So of these equations, you have to decide which one do we want to use. To me, it seems that since we know the initial velocity is 0, we can just cancel this variable out and make that problem easier to solve because we wouldn't have to use the quadratic equation to solve for time. In this case, you do not have final velocity, so that would just be additional work to try to find that and then plug that into this equation. Instead, you can directly solve for time by using the equation on the left. So let's go ahead and do that. Delta y, which we were given is 120 meters, is equal to 1/2, and in this case we're given the gravity constant, which is negative 1.5 meters per second squared times t squared. And actually, in this case, I made a mistake. Because our axis, or the gravity constant in our problem is negative, we're told that the axis shows that positive is up and negative is down. Because if a gravity constant is negative, which is a force that's pointing downward, that indicates to us that the negative part of the axis is pointing down. So that would mean if you're dropping something down a 120 meter deep crevice, then 0 is up here and 120 meters is down here, right? So our 120 meters should be negative. Once you do that, you solve for time. And if you didn't catch it then, or while you were doing the problem, you would probably catch it later when you realize you'd have to take the square root of a negative number, which would not be possible for when solving for a time value. And this would give us an answer of 13 seconds when accounting for significant figures.